The project of ME221 demo modules consists of team members Alyson Cole, Jenna Glass, Rohloff, Matthew Zastoupil, and our mentor, Dr. Amiri. A core course in engineering, especially at North Dakota State University, is ME221, Engineering Mechanics 1 or Statics. In this course, students learn about many basic concepts of statics such as vector components, forces and moments, support reactions, and friction. The problem is many students still struggle to visualize these topics. This lack of visualization can prevent them from understanding many statics concepts, which become the baseline for most future engineering topics. For this problem, we designed 3 demonstration modules that cover the 4 basic concepts previously stated. The modules will be used to demonstrate different examples of these concepts for future ME221 students at NDSU. The modules should be easy to set up, user-friendly, large enough to see in larger lecture halls, while being adjustable for multiple demonstrations. The design targets were based on the fundamental principles of statics class and our ability to demonstrate these.
Concepts were designed, revised, and chosen through a process of screening and scoring. The final designs were modeled in Creo. The manufacturing and assembly process was continuously occurring as purchased materials arrived. It can be broken down by module. For vector components, T-slot framing rail was cut down to 2-foot pieces to represent the X, Y, and Z axes. A ball socket joint with an extending radio antenna represents the vector component where the angle and overall length are adjustable. Work badge clips slide along the rails and can be locked into place. The 90-degree angle becomes visible when the strings are attached to the end of the vector. To demonstrate the shadow method, a light was secured on the vertical rail. The angles to the axes can be measured with an external digital angle finder.
The friction module consists of a 2 and 3 foot board that were connected with a hinge and fabricated brackets on each side to allow the board to sit at any angle. 4 wood blocks are then cut down and milled into carts with wood, carpet, vinyl, and metal as their frictional surfaces. The cart is set on top of the board with a known mass. The board is set at an angle. When the cart slides down, the angle is fixed and noted. Students can then calculate the coefficient of friction for that material. Another demonstration records the maximum force it takes to pull a cart up a ramp. A motor pulls the cart, the max force is recorded using a load cell where it is then displayed on a digital screen. All programmed using Arduino coded with C++. This required testing, calibration, and soldering to get all the electrical components operating properly. The final module is forces, moments, and support reactions. To demonstrate this, everything is attached to a plastic sheet and more framing rails. For the support reaction, the pin and the roller were modeled in Creo and then 3D printed. A fixed support reaction was constructed with wood. A motor with a mechanical arm that applies a force vertically downward is controlled with buttons. The beam receives force with load cells continuously reading the force that is applied. The forces from the pin and roller reactions and the moment from the fixed reaction is then displayed on digital screens. The coding and testing process was similar for this module. The third concept on this module was the equilibrium of a particle.
Overall, the modules are great visualization tools and big enough for students in the lecture hall to see. They are customizable for different examples so that students can get a thorough understanding of each concept by seeing many demonstrations. Some recommendations for improvement include a more efficient code that improves component functionality, new material for friction boards due to warping, and having a cover to go over electrical components on the friction board. Thank you to the following.